If my time is showing properly, it's the time for the next talk from Greta Panova. The title of the talk from University of Southern California with the title The World of Poset Inequalities.
Thank you very much. Thank you for inviting me and having this really nice conference happening still online. Here where I am, it's 8 a.m. and I'm usually asleep at this time, so you'll excuse me. I haven't had maybe enough coffee. So what's this talk about? Of course. Let's see. Okay, so we all know in combinatorics what partially ordered sets are. This is a set of elements, in this case A, B, C, D, and some partial order between them. So we know that A is bigger than B, C is bigger than B, C is also bigger than D here, but we don't know we don't have any other restrictions. And so we like to make things into permutations. So from this poset, we can make linear extensions, which are actually permutations of these labels. What are the linear extensions? Are assigning numbers from 1 up to n. N is the number of elements in my poset, so that these numbers actually respect the ordering. So when I assign the number 4 to A here and B to and 2 to B here, then 4 should be bigger than 2 as it is, because A is bigger than B. And so here are all possible such assignments. In this case, we have 5. So you see this all the time, depending on what structure you actually work with. And of course, this is enumerative combinatorics. We count how many linear extensions there are. So here are a few examples. So if we have a chain, all the elements are ordered. There is only one way we can arrange the numbers from 1 to n in increasing order. If we have an anti-chain, then we have no relation. We get all permutations and factorial of them. If we have 2 chains, we just need to choose which elements go in one chain, and then the others will go with the other chains, and then they will be totally ordered. So then we just have to choose these elements. So this is a binomial coefficient. So m plus k, choose k for m and k chains. Then we have our favorite Catalan poset. So if this is our partially ordered set, so these dots here are our elements, then this is a 2 by n Young diagram as well. It corresponds to lattice paths above the diagonal. So there are many interpretations for these numbers, but in the end, the number of linear extensions is our favorite Catalan number. And here, this zigzag poset. So we have some elements that are bigger than their neighbors. If you assign numbers here and you read them along this snake, then you get an alternating permutation. And what's the alternating permutation is counted by the Euler numbers, and we know that the exponential generating function is secants and tangent in this case. So we cannot immediately, we can throw out the hope for any closed form formula in general. And yes, and in general, this is phrased in terms of complexity, that counting linear extensions is sharply complete. So there is not going to be a polynomial time algorithm. This is a hard problem. There is not going to be a nice formula. And in fact, even just height 2 posets, like in this case with the zigzag poset, it's still sharply complete. Okay. So now there is no formula. What do we do? So we don't give up yet. So we still can try to study posets and linear extensions, and this is, so when there is no exact formula and an equality, we go to inequalities. So let's start with a motivation with a famous problem, which is about sorting probabilities. If we have 2 elements x and y in our partially ordered set, we can talk about the probability of one element appearing before the other, or having a smaller number than the other, in a linear extension. So don't be scared by the word probability. And for combinatorialists, this is just the ratio of the total number of linear extensions for which the value at x is smaller than the value at y, divided by the total number of linear extensions without any restriction. So here is an example. Here is a very simple poset on 3 elements. Here are all these 3 linear extensions. And what is the sorting probability that C is smaller than A in this case? Well, in 2/3 of the cases, C is smaller. And in fact, this is an extreme case. It turns out conjecturally, so it's a really old conjecture, as you can see here, that for every finite poset, which is not a total order, which is so not a chain, there exist 2 elements x and y. You can find them somewhere such that the probability that x is smaller than y is between 1/3 and 2/3, or in other words, the number of linear extensions for which Lx is less than Ly is at most twice the number of linear extensions in which this order is reversed. And as you can see, their equality is achieved, but so far, what the known cases where equality happens on either way of this interval is when the poset is comprised of some smaller posets of this form.
The conjecture was made independently by these people?
Yeah, I think so, because back in the days there was no internet and maybe people were not aware, so
Okay.
easily aware. And it was in different contexts also. So it originally came from computer science. And it has to do with sorting algorithms, as you can imagine. So here are some results since then. So this is the survey, the paper of Brightwell, Felsner, Trotter from '95. They say that this problem remains one of the most intriguing problems in the combinatorial theory of partially ordered sets. And here are some results. So this is actually pretty close, and there is some improvement. So there is, this is with some geometric methods, but this here, I mean, eventually there are geometric methods, but I will tell you what kind of ingredients come into the proof of this result here without actually proving the whole result. So we want to do other things in this talk. And so here are some special cases that have been done. So of course, for algebraic combinatorialists, we like Young diagrams. So, and the standard Young tableau are linear extensions on the poset of the Young diagram. So this problem is absolutely natural for us. Okay, so this is motivation. I'm not going to solve this problem in this talk, so suspense down, but let's see what we can do. So here is again the definition of sorting probability. Here is an example, as I said, with our favorite Young diagram. So the partially ordered set is on these boxes, and the orders goes. Elements should be increasing along rows to the right and down columns. So here are the 5 possible assignments of the numbers from 1 to 5. These are standard Young tableau. And if we choose 2 boxes, the red and the blue one, then we can talk about the probability of the blue being smaller than the red versus the red being smaller than the blue. And you can see that so I reversed it, so it's a -1/5. So this is the first case is on the bottom and the second case is on the top, and so we have 1/5 probability. So this conjecture holds, no surprise. So another conjecture, actually much in some sense stronger, but maybe less general in the sense of every special poset, should hold that if we take a partially ordered set of elements and somehow we make it grow as with some measure, and so that the anti-chain, the largest anti-chain, which is the width of the pulse, goes to infinity, then this sorting probability should actually go to 0. It's not just smaller than 1/3 by that conjecture, but it actually goes to 0. And so this is when we take over all pairs of elements x and y, we take the minimal difference between these two probabilities. And this has been proven when we have a very big anti-chain. So n over log n is a very large proportion of the elements of our partially ordered set. So what we did is we proved it for Young diagrams, like in this picture. So the Young diagram can grow linearly in the rows with n, and then this sorting probability is smaller than c over square root of n. And of course, for the Catalan pulset, we actually have even better bound, and this is because we have a lot of formulas for actually computing things more precisely. So this is one way we can continue our study of partially ordered sets and their linear extensions. But this is, since this is enumerative combinatorics, we are not going to do things asymptotically this time. We're going to actually try to be more precise as much as possible. So let me show you what kind of ingredients showed up in the proofs of this earlier results in the 1/3, 2/3 conjecture without going into details how this works. And the type of ingredients that showed up are this following log concave inequalities. So one is due to Richard Stanley from 81, where he was using Alexandrov-Fenchel inequalities from convex geometry, very not combinatorial in some sense, to prove this inequality, this log concave inequality. And k here is the number of linear extensions such that the value of this particular element, so we fix some element x in p, we look at all linear extensions for which the value at x is equal. Let's go.
Sorry, I fixed that.
Okay. All right. So so this log concave inequality says that nk squared is greater than or equal to nk minus 1 times nk plus 1, or while log concave, if we take logarithms on both sides, then this function is concave. So this log of nk is actually a concave function. And so here are some generalizations of this fact. So if we have two elements x and y, we want to count the number of linear extensions such that L of y minus L of x is equal to k. So they are k steps apart. Then we still have a log concave inequality. And again, it's proven with non-transparent Alexandrov-Fenchel inequality. So we gave a different proof, a completely combinatorial one, but this is in the case of with two pulsets. So the pulsets which are somehow composed of only two chains can be cut into two chains. And then there is also this cross product inequality, which has not been proven in generality for any with any means. This is now if we have three elements x, y, and z, then FKL is the number of linear extensions such that the difference between the value of y and the value of x is k, and the difference between the value of z and the value of y is L. And then, so we have now two parameters, k and L. So this is, so if we increase or decrease both of them, then we actually decrease this product value. And okay, so here are a bunch of inequalities, and so I'm not going to prove this here. I'm only going to show you a little bit how this one works combinatorially, so the Stanley inequality, so you have some idea what kind of methods can be used and see some combinatorics. But before I continue, so let me give some motivation of why we should study log concavity to begin with, and that's so after this summer we can motivate it even more easily because of the Fields medal, which was given to Jun-Hyu. So he developed a lot of theories for proving exactly log concave inequalities. For example, this Mason conjecture states the following. So as you can see, it's exactly the same form as the previous inequalities on the previous page. So in this case, this is an inequality for matrix, and I'm not going to talk about that at all. So I'm just advertising the whole area of log concavity. So how do we prove combinatorial? So all these proofs so far, even Jun-Hyu's proofs, are not using any kind of explicit combinatorial bijections, injections, and things like that. So let me show you a few. So let's start with two posets in this case, but this works in general. So we have two chains in our poset, and here the red numbers are linear extensions. So these are alpha and beta are our elements. These are the values that we are assigning at our elements. So beta 1 has the value 1, alpha 1 has the value 2, and so on and so forth. The black line means that all the arrows go down. Also here, all the arrows go down. These are extra relations in our poset, the blue and the green arrows. And now we can make from this linear extension, we can make a lattice path. How do we do this? Well, we start reading the numbers here, and if this is going to be our first chain, the alpha and beta is going to be our second chain. And if we read a number from the second chain, we make a vertical step, and if we read the next number from the alpha chain, then we make a horizontal step. So let's do this. So here is the number 1. It's the second chain. So we start our lattice path. The first step is going to be up. Then we are in the first chain. Then the number with the number 2. So we make a horizontal step. The number 3 assigned to alpha 2. So it's still a horizontal step. So the third step of our lattice path is horizontal. Then 4 is on the beta chain, we go up, and so on and so forth till we read off all the numbers up to n, in this case 14. We reach the end of the square in this case. And what is the full correspondence? So which lattice paths correspond to linear extensions? It's exactly the ones which are contained in this white region. So these relations are drawing out two boundaries which we cannot cross. So all linear extensions are correspond to lattice paths inside what we call a monotone region. Monotone because the path goes up and down only. And here again, the path of the boundary only goes up and down. So we are going to consider lattice paths in a region if you have a larger anti-chain in your poset, then you have to go in higher dimension, but still this will still work. What may not work in higher dimension is now the following bijections and injections that we actually do. So this is an injection about lattice paths. So don't read the long statement. We can actually just see how the injection works. So we take two lattice paths from pairs of lattice paths from A to C and from B to D. There is some region in which they live. And then from this, we are going to create a pair of lattice paths from A prime to C and B prime to D. So the red, we are going to go from the blue to the red paths. And this is going to give us, this is an injection. So if you have an injection, we have an inequality that the number of these paths is less than the number of these paths here, the red ones, pairs of paths in this case. What is the injection? The injection is that we have to slide vertically the lower path until it starts to point A prime here. Then we find the first intersection. So they're definitely going to intersect because of the conditions on how these points are situated with respect to each other. And here the point is that the A and B are farther out than A prime and B prime. Once we find this intersection point, then we do like in the Lindstrom-Gessel-Viennot lemma for counting non-intersecting lattice paths. We actually reassign this path. So now we trace the lower path. The red path becomes the path from A prime to E and then from E to C. And then the other path is, well, if we do the same operation down, we will get also the red path. So this is how this injection works. We can also do this even if the paths are not between two vertical lines, but between a horizontal and a vertical line, we can still find some inequalities. Now, if we have such injections and such inequalities, we can actually prove Stanley's theorem and actually add a Q analog to this. In the case that we have just the poset is comprised of two chains, the alpha and the beta chain. So what is the Q analog? The Q analog, in this case, we can take the statistic is Q to the sum of the values at one chain. And what does this correspond to in the geometry? So this actually corresponds to the area under the lattice path. And so this cutting and pasting of lattice paths that we're doing are actually preserving the area. We're doing some vertical translations. We are actually preserving the area. So we actually have an inequality for this Q polynomial. So the inequality is coefficient-wise. So if we expand this as a polynomial in Q and this also is polynomial in Q, the coefficients here are greater than or equal than coefficients here. And so here is how the proof works. So basically this term corresponds to paths that go from 0 to Q, and they pass through some middle horizontal segment A1 prime, A prime here. And then these terms, these terms are pairs of paths. One is passing one step above and one is passing one step below. And so by the lemmas that I showed earlier, if we have an injection from the pairs of paths that are passing further out into pairs of paths that are passing closer to the middle. And so we have an inequality. So this is by the lemma. And this is also here, this picture is showing when equality arises, and this is why it's actually nice nice to have such injections because you get, you can derive the equality case. And so this is the equality case, and this is another application for non-intersecting for random walks, even actually self-intersecting random walks in a monotone region. We cannot count them in general if we don't know what the specifics of the region are, but we can still say that the probability, the exit probability of one walk on a certain point, vertical point K on the left, on the right boundary is still log concave. So we still have this type of inequalities here. So I have five more minutes. So let me briefly tell you how further this generalizes. The way it generalizes goes to the order polynomial of P. So this is how linear extensions generalize naturally for combinatorialists. Instead of assigning the numbers from 1 up to n like a permutation to the elements, we can assign any number from 1 up to t. So we make a function from the posets to the numbers from 1 up to t, and it should respect the order. So it should be weakly increasing whenever the element x is smaller than the element y in P. And it turns out, as a function of t, so the number of values that this g can take, this is actually a polynomial in t. This is the leading coefficient is the number of linear extensions over n factorial, and then there's some other term. So it already contains a lot of our information. Here are some examples from earlier. So here are our linear extensions, our posets, and this is what the order polynomial looks like. So this is a generalization of these particular numbers. And so now we can ask so for the order polynomial, again, same problem. We don't have a formula in general. And in fact, we don't know, the coefficients are not always positive. And because the coefficients are not always positive, this inequality, so this is the leading term, is not actually obvious. Or at least I'm not aware of it. So here is an inequality for the order polynomial. It's bigger than or equal to its leading term, again, because the other coefficients, next terms, could actually be negative. And the way we prove it is by an injection again. So if this is this take-home message from this talk is that one can prove inequalities by injections. And if you have an injection, you might have some interesting inequality at hand. And the way the injection works is we take a linear extension, and we take, so t to the n in my book is going to be possibly empty set partitions of n. So in this case, 2, 3, 7 take the value 1, 4, 6 corresponds to our second set. There could be an empty set, of course, and then 1, 5 is our third set. And from here, we get an order preserving map and a permutation. How do we do this? We take, we take our linear extension. So the first set has 3 elements in it. We don't care what they are at the moment, but we look at the first 3 values of f. So 1, 2, and 3, we label them here with 1s. Then our second set has 2 elements. What are the next 2 values of f? These are 4 and 5. We label them with 2s. And then the third set has 2 elements. So the next 2 values of f are labeled with 3. So we get an order preserving map. And now somehow we need to remember what was going on here. And this is how we get a permutation sigma. So sigma, as you can see, is a permutation where the elements in the first set appear first, then the elements in the second set appear second, and so on. And how they are permuted would actually depend on how how these elements that we all label them 1 in F are arranged with respect to each other. So we actually have complete information of where we came from. So this is an injection. And so in particular, if we take the difference on both sides, we actually get a bunch of things that are not or do not correspond to this setup somehow. So we actually have some kind of a combinatorial interpretation for them. And there are some other inequalities we can do. So this is another different type of inequality for the order polynomial, which does not follow from the previous inequality. And this one, unfortunately, is not entirely combinatorial. It uses the FKG correlation inequality somewhere in the proof. So this is still, in some sense, open to proof combinatorial. And since I'm out of time, I'll stop here. So there was a bit more, but thank you very much.
Thank you. Thank you very much. And the time for questions.
I have one question.
Yes, go.
Yeah, related to these inequalities for the random walk probabilities, what are some conclusions or applications of these inequalities? Do we have some other probabilistic results we need such inequalities?
Not yet, but I would be interested to see some. So we got this for free from the injection, but it's. So these log concave inequalities, they can be used to prove some actually more quantitative results. And but so far we haven't seen a problem actually to apply them to. So if you have one, I'd be curious.
Yeah, I just wondering, can we say something about the long time behavior of these walks probabilistically by using these inequalities, or is that just?
It might be possible. Yeah, so one has to think about this.
Okay, thanks.
Other questions?
Yeah, I have a question. A log concavity condition can be expressed as a certain 2x2 determinant being non-negative.
Yes.
So can you extend it to higher versions?
It's not true anymore.
Oh, so it's, okay.
We tried, yes, that's a very natural extensions. We tried, and this is not true. There is a poset where if you take the 3x3 determinant is no longer.
Is it true in special cases, in some special cases, or it's never true?
Oh, I mean, yeah, it works. I mean, of course, if we take just several chains, it's going to work, I think. But it's if you take it a little bit away, then you just introduce one more relation and it already fails. So
thank you. Too bad.
Other questions? Well, if not, we thank you, Greta, for your wonderful talk.